So chapter 12 is liquids, solids, and intermolecular forces. We're going to learn about the types of intermolecular forces as opposed to intramolecular forces. Now, we already learned a plethora about that. So intramolecular means in between atoms in a molecule. So we've done that already with covalent bonds. We know everything about them. Ionic bonds, we know everything about them. But now we have these types of interactions that are not forming molecules, but they're forming substances that have billions and moles of the same molecule or different molecules mixed together. And how are those molecules interacting? For example, why is maple syrup a different viscosity than water? Why is oil and vinegar, why is an oil and vinegar mix? Why is vinegar, or why is oil, if you leave oil on the floor, it stays there forever, for a long time. We'll learn about that. So like it has to do with these, all of that stuff and more has to do with intermolecular forces. So does the boiling point, the melting point, all the condensation, vaporization pressures, all these different things have to do with intermolecular forces. So there are 3 types of intermolecular forces, technically 4 if you're talking about biochemistry, but there's 3 here in just chemistry. First one is the London dispersion force, otherwise known as van der Waals interaction, and it is very weak, and we'll learn about that one as well, but we'll learn about that one first. Second, dipole-dipole interaction. So it involves anything that has a partial dipole and a dipole and a dipole, basically. We learned about what a dipole is because it's a polar molecule that has an unequal sharing of electrons, such as water. So water and another water will form a hydrogen bond, which is a special type of dipole-dipole interaction, which we'll learn about. And then we have ion dipole. So if you have a salt, such as Na plus and Cl minus in a solution, and the Na could interact with an organic compound that is a dipole. They're not going to bind chemically, but they're going to interact. And this happens all the time in biochemistry or different kinds of buffer solutions where you're dealing with proteins and things like that. Okay, so basically all of these forces attract molecules or even repel by the same principle. The principle is, if you look at each molecule as a blob, the blob has electrons flowing through it. They're being shared, they're being transferred, whatever. It has electrons in it. Think about them as balloons of electrons just smashing against one another. If you have something like a dipole, that's shown in the first case up here, 2 dipoles have a plus and a minus charge. They interact with each other and they will stick and attract each other in the plus minus configuration. The pluses will be next to the minuses. So that will be opposites attract. That's that. That's how dipoles work. And it's because the electron-rich region that's negatively charged will interact with and bond and stick to the electron-depleted region of the neighboring molecule. This is in general, these intermolecular forces are a lot weaker than covalent and ionic bonds. So where covalent and ionic bonds take hundreds or even sometimes thousands of kilojoules per mole of energy to break, these bonds require maybe 20 or maybe 100 at most kilojoules per mole. Well, no, less than that, like 5 kilojoules per mole to break. Really not much. And that amount of energy to break them directly corresponds to the boiling point, because the boiling point temperature is the average kinetic energy of the particles. So it all relates. That's a dipole-dipole. That's the principle. And same thing for a hydrogen bond, which is a special type. The next is a van der Waals, or we'll call them dispersion. Now, the dispersion force, and also dipole-dipole is, they're polar molecules. Keep that in mind. They're all polar molecules. A dispersion force happens between non-polar molecules. Oh, how can this happen? How is there any kind of electrostatic interaction? All these interactions are electrostatic. How can this happen if both of them are non-polar and not charged? The answer is the idea of the induced dipole. What does that mean? Well, the induced dipole is, let's say both of these electron blobs are hit, they're really neutral, there's no dipole. They hit each other. When they hit each other, their electrons get jumbled up and they shake. When they shake, for a moment of time, the electrons from one of the blobs or one of the molecules gets kicked around in the molecule and moves to one side of the molecule. At that moment in time, the molecule is a dipole. The dipole of this molecule was induced from a collision. So we call it an induced dipole. So that's exactly what this picture is showing. There's a collision. The momentary collision moves the electrons of, let's say, this one to the back. That momentarily, for a very short amount of time, makes the front of the red one positive, meaning the next door neighbor molecule will now see that positive, and all of the electrons from that molecule, which was originally neutral, will come and scurry towards that end to get close to the positive. But then, once this is a very weak interaction that happens a very short amount of time. But it creates not completely inelastic collisions, or completely elastic collisions. It doesn't. This is what happens when gas molecules hit together. So remember that assumption of the kinetic molecular theory of gases, that gases are completely inert and don't react with one another? That's not true. They go through these dispersion forces, but they are so weak, we can make them negligible in some cases, in most cases. In biology, it's different because a lot of them are important for compounds or little molecules binding to proteins. But in chemistry, another thing is, gas molecules are moving a hell of a lot faster than proteins. So because they're moving so fast to begin with, that reduces the time that these molecules are even in the same vicinity to go through this dispersion force. So that's that. But they all follow the same idea, that either the dipole was there to begin with, or it's induced from some kind of collision or some kind of chaotic event, which then allows the pluses to go near the minuses of neighboring molecules. Okay, so let's just cover that in words. Dispersion forces. So the temporary dipole, the attractive forces caused by temporary dipoles is called dispersion forces, aka London dispersion forces. All molecules have them, technically. It doesn't only have to be nonpolars, but polar molecules exhibit them too, but the effect of them is maybe 0.0001% when compared to the dipole-dipole. So we consider them to be negligible when we talk about water bonding to another water, a hydrogen bond. But for nonpolar molecules, they're the only interaction that occurs. So they have to be mentioned. That's important. Okay, any questions on dispersion forces? Okay. Moving on. Size of the induced dipole. So if you have this kind of, this is the opposite of what we learned about bond strength inside a molecule. So we learned general concepts. If you have a smaller atom, then it's going to bond stronger to another one since the nuclei are close together. That no longer applies for intermolecular forces. For intramolecular forces, definitely. But for molecules interacting with each other, which is different than atoms interacting with each other, the larger the atom or larger the molecule, the more electrons it has, the more electron density, meaning the more electrons it can move around, meaning the increased polarizability. That's a new word. So polarizability means how much can it become charged? And if it has more electrons, a larger electron cloud, it could be charged more, therefore making stronger interactions. So if you tell me which one will create a stronger dipole or a stronger van der Waals force, CH4 or C3H8, propane versus methane, which one? Or methane on the left versus propane, which one would create the larger induced dipole? Which one would be a larger attraction to another nonpolar? Yep, this one would be larger because it has, or really it's now taking in the other variable is the shape and the size. So we're not really the shape meaning the surface area. The bigger the surface area of the molecule, the more interactions it can make with nearby other molecules, with other molecules nearby. And the larger the size, the more electrons it has, meaning the larger the molar mass, the more electrons it has. So those two things, the mass and the size, and really the surface area, are important. So effect of molecular size on size of dispersion. Helium, yeah, so the boiling point, and the reason why we use boiling point as a metric, the boiling point is directly proportionate to the intermolecular force amount of an element. So if, let's say, or of a molecule in general. So let's go back to this methane propane example. So between these two, which one do you think will have a higher boiling point? Yeah, C3H8. Why? It's bigger. It partakes in more molecular or intermolecular interactions, more dispersion forces. And the same with these noble gases. The smallest one, which is helium, will have the lowest boiling point because helium atoms only have 4 electrons. Only have 2 electrons. Molar mass is 4. They only have 2 electrons. These 2 electrons will be moved a little bit, but that charge that'll be created, that induced dipole, will not be very big in comparison to xenon, for example. So that makes helium have a very low boiling point of 4.2 Kelvin. So you ever heard of I've heard so those of you who are talking about who like computers, people who are into extreme overclocking, they usually use liquid nitrogen, but there's some videos on YouTube where they use liquid helium to cool the CPU, and that's a step above, and it's incredibly more expensive. It's terrible to do. It's like, I'm not saying it's terrible to do in general because helium is really, really expensive, and the world is actually running out of helium, so to waste it on stuff like that is not good. But yeah, but it's very cold. Like liquid nitrogen, for example, is, I think it's negative 122 Celsius on average, but I don't know what that is in Kelvin. Liquid nitrogen temperature. Negative 196 Celsius is the boiling point. So anything under that. So negative, it'll be in like the 70, 80 Kelvin range, which is still really cold, but for like 60, 70 Kelvin range, whereas helium is in like single digit Kelvin. So that's crazy. All right. So here are some boiling points and melting points of different organic alkanes. So I've already mentioned 2 of them, methane and propane. And we said that propane and methane, or propane has the higher boiling point. It also has the higher melting point. So really, the larger the molecule, the bigger the surface area, the more interactions it has, or it can have, the more energy required to break their intermolecular bonds. Meaning the higher the boiling point and the higher the melting point. You want a shortcut? Bigger the structure, bigger the melting point and boiling point. Done. Also, surface area matters. So here's N-pentane versus neopentane. Now, the reason why N-pentane has a larger boiling point is because it has a larger surface area. So it's longer. It can have more potential bonds with other molecules that come in close contact. Whereas neopentane is kind of like a ball, which is kind of like some of the atoms' surface area is stuck in the middle, and it can't really partake in all those bonds or all those intermolecular forces. So same thing. Okay, then we have the dipole-dipole attraction. Now the dipole-dipole is when you have polar molecules interacting with one another. And this one's fairly easy to understand. I'm not gonna go crazy with it, but polar molecule, what do you have? You have a minus end, you have a plus end. The polar molecule from another element, or another molecule, sorry, or wow, the positive and minus from another molecule will come into contact in this kind of arrangement, in a plus minus. And that's it. So polar molecules tend to have a lot larger boiling points and melting points than nonpolar molecules. Why is that? See if anybody was listening to what I said. Boom, exactly. So dipole-dipoles are stronger, or the strongest type of intermolecular force, a lot stronger than van der Waals, or London dispersion, sorry. I use those terms interchangeably. They're the same thing, but this textbook uses London dispersion. And Adi has a question. So where does helium naturally even form? Good question. So helium is actually formed in the sun by the nuclear fusion of hydrogens. That is how the sun gives off radiation from forming helium. And then, so I was watching, that's the only way. I think so. Maybe like supernovas and stuff, like they blow up and a lot of stuff comes out. Maybe helium's there too, but a lot of it's iron. I know that. But yeah, so basically the way the sun dies, actually I was learning about this. I was watching a YouTube video like 2 weekends ago at like 2 in the morning. It was just like, oh, how does the sun work? I'm like, oh, cool. I watch it. But I knew like the reaction stuff. But when the sun dies, that means all of the hydrogen is converted not just to helium, but all the way, it makes nuclear fusions all the way to get to iron. And when most of the internals of the sun is iron, and all the hydrogen's been depleted, that's when it goes into like a supernova, and then, or what we call a neutron star, whatever, one of those things, and then it like dies and then explodes. So, cool, good to know. And yes, Ed, yeah, those are the best 2 a.m. YouTube videos, exactly. Their algorithms are on point. Like during the day, it's like, I mean, I don't even really watch YouTube during the day, but if I do, it's like stupid stuff's recommended. But at night, it's like cool stuff. All right. Okay, I'll ignore the comments. All right. So dipole-dipole, we get the point. Attractive force and solubility. That's another thing. So if you have polar molecules, they will dissolve polar molecules. So like oil and water don't mix because the oil is nonpolar, water is polar. So that's a good thing to know. And the technical terms is if something is miscible, miscible liquids will always dissolve in each other. Miscible means they mix together. Yeah, so polar solvents dissolve polar, whatever. Okay, we get the point. And nonpolars dissolve nonpolars. So in organic chemistry, we do a lot of that. So for example, I'll tell you about what I've been doing lately. So I've been doing a lot of organic synthesis, which maybe some of you will get involved in undergrad. And for me as a biochemist, it's new to me because I've done organic chemistry labs and stuff, but I haven't really gotten into creating new compounds that no one's ever done before. And that's what I'm doing now, to try to make new drugs. So we take advantage of polars dissolve in polars and nonpolars dissolve in nonpolars. So one very common technique is an extraction. So let's say one time I had a product, something I was looking for, and it was stuck in, it was supposed to be, this is all organic compounds, right? Because all drugs are organically carbon based, just like we are. That's how it can be miscible into us, right? They're all carbon based. So this molecule it's pretty polar. So but it's there's a degree of polarity to it, and it's pretty polar, but it should still be miscible in nonpolar solvents. So it was stuck in the polar layer, right? It's stuck in polar solvents and water and like methanol, things like that. So what we do to get it into the organic, into the nonpolar stuff, is we can use nonpolar. There are solvents that actually dissolve in both. So they're kind of like half polar, half nonpolar. So some that are like ethyl acetate is one of them. DMSO, dimethyl sulfoxide, is another one. So we use kind of, and also what did I use? DMF is another one. There's a bunch, but I use, and also we can make our own solvents. We can combine them. So I use dichloromethane, which is very nonpolar. So I'll draw dichloromethane. So it's like, looks like this. It's basically methane with 2 chlorines on it. And I can mix that with methanol, which is pretty polar. So methanol looks like this. And you can make a mixture of, what we do is 90% dichloromethane and 10% methanol. We mix that with our really polar solution that has our compound in it. And if we mix it enough, our compound actually comes out and sticks with this solvent, the 90%, 10% solvent, and we could extract it that way. And it forms 2 different layers. So you have normally you have an organic layer and an aqueous layer, you call them. The aqueous layer is the polar layer. The organic layer is the nonpolar layer. So, but the idea is with the solvents, the reason I'm telling you is there's a whole degree of polarity. It's not just one's polar, one's nonpolar. There's a whole degree in the middle. And you can use that degree to your advantage depending on what experiment you're trying to do and what compounds you're trying to make intermolecular forces with. So the reason why I'm doing these solvents is you want to make intermolecular forces with the molecule in question, or the molecule that you're trying to dissolve. You're trying to make forces with it to bring it out of wherever it was. So that's pretty neat. Okay, so hydrogen bonding. Didn't even talk about this slide yet. Hydrogen bonding is a dipole-dipole, but it's the strongest one by far. So it is a specific type of dipole-dipole that is stronger than the other ones. And the reason why it's strongest is because hydrogen is the nonmetal with the lowest electronegativity. And we know that. It's only 2.1. Because of that, and also it's very small. Because of those 2 things, when you have hydrogen in one molecule binding to another molecule with a big electronegativity difference, such as with oxygen, nitrogen, or fluorine, you have this insanely strong dipole-dipole, which it's so much stronger than the others, we call it its own class, which is called a hydrogen bond. So for example, in water, you'd have a hydrogen bond between the hydrogen of one molecule and the oxygen of the other. So because the oxygen will be partially negative, the hydrogen will be partially positive. These will form a dipole. Also, let's say you had some hydrofluoric acid in here. Same thing will happen. The hydrogen from one will form a hydrogen bond with the oxygen from the other. And the reason why this is so strong in comparison to normal dipoles is because look at the difference in electronegativity here. HF is huge. Like F is a 4.0. He's a straight A student, he or she. Mr. and Mrs. Fluorine, they're straight A students. And hydrogen can barely pass his classes, he's 2.1. It's funny that, I just thought about that. The electronegativity is like a GPA scale. The highest is 4. And the lowest is they have like what are they, like 0.3 or 0.4 is the lowest. But you guys don't have to worry about that. You're all getting A's, right? Hope so. If it was up to me, I'd give everybody A's, but that's not how it works. But anyway, so do you get how this works? Any questions on that? So the fluorine negative is going to be hugely negative, and the difference is going to be huge. Therefore, the charge difference is going to be huge. So that means the interactions it makes with neighboring molecules is going to be huge. So we see that there. We see that in water. Relationship between H bonds and intermolecular attractions. So all of our hydrogen bonds, you see the boiling point is really high. All these three would form hydrogen bonds. NH3, HF, and H2O. In comparison to the other ones, they're very low. That are very low. You can have actually a stronger one, a stronger intermolecular force. This is called the ion dipole. So ions, we know plus or minus, they are stronger than a dipole's plus or minus end. So if you intermingle water with, let's say, a salt, NaCl, you'll have ion dipole interactions. And we've seen this before when we talked about solutions, and we said water dissolves the salt particles by ripping apart the Na plus from the Cl minus. That's exactly how ion dipoles occur. And you see that interaction, but the key thing is they're not chemically bound. These are intermolecular forces, meaning they're not, the water is not making a covalent or ionic bond with the chlorine minus. It's making a simple ion dipole attraction force, which is an intermolecular interaction. And it's weaker than a normal bond, as we said. Okay. But there's just a summary of all the bond types. Liquids. Okay, liquids. All right, vaporization. All right. If you have water, you have, let me see. So if these molecules are at the surface, they may have enough energy to overcome the attractive forces. Yeah, I mean, so this is where we get evaporation. So if you have water, we all experience water, and you leave it on the table, you spill it, it evaporates if you leave it there. It takes a while, depending on how much water you have. But evaporation is simply from the surface molecules gaining enough energy from the collisions from the outside air to gain enough energy to leave the solution and to break those intermolecular forces. That's all evaporation is. Boiling is we're using energy to break apart those intermolecular forces at a certain threshold temperature or a certain threshold kinetic energy, which shows that temperature and kinetic energy are the same thing. At that certain threshold, then the molecules will now become in the gaseous form because their intermolecular forces will break. And we can always figure out the energy of vaporization. So if something requires a lot of energy to vaporize, then it will have a low vapor pressure. So we'll talk about vapor pressure next. So the weaker the attractive forces, now we're going to talk about some associations. And this makes sense based on what we just said. The weaker the attractive forces, the faster the rate of evaporation. So water has pretty strong attractive forces, right? Hydrogen bonds. It takes a really long time for it to evaporate because it takes a long time for those neighboring molecules in the air to kick off or to break those intermolecular forces of the water in comparison to something like who's ever nail polish remover, who's ever experienced nail polish remover, basically acetone, right? So what happens is if you spill it on the table, you wipe it with like a towel, it's gone. It's already gone. It's like it's not wet anymore. Like, whoa, where the hell did it go? So it is a very high vapor pressure. We'll talk about in the next slide, but it has very weak attractive forces. Acetone looks like this. So it's very nonpolar. Well, there's a little bit of polarity there, but it's pretty nonpolar. It's symmetrical this way. So it's nonpolar. And what that means, the more nonpolar something is, imagine the more dispersion forces it'll have, meaning the weaker the interaction it is, or I'll say it this way. Small nonpolar molecules will have the fastest evaporation because they'll have the weakest attractive forces, kind of like we went over already. And something that evaporates easily, we call it volatile. Something that does not evaporate easily, we call non-volatile. So volatile means it enters the air quickly. That's not good because it becomes a gas. And that's why in organic chemistry, as opposed to Gen Chem in the Gen Chem labs that unfortunately you guys didn't experience. But what you do is in organic chem, you're always doing your work under a fume hood. And the reason why is because you're dealing with mostly organic solvents or mostly non-polar solvents. These solvents have very high vapor pressures, meaning if you spill them on the table, they're going into the air really quickly. So you want to have a fume hood to suck all that in rather than getting it in your eyes or ingesting it, getting it in your lungs, stuff like that. But then you become a TA and you just become immune to chemicals because you've exposed to it so much. Now I can't see anything. No, I'm kidding. Anyway, condensation. So the same thing can happen with not only evaporation, but condensation when you're taking the gas molecules and they lose energy to become a liquid. So this happens, let's say in the morning dew, right? The air is really hot during the day in the summer. In the morning, it's kind of cold and you go outside, the grass is soaking wet. That's because of all the water vapor from the air is now condensed and become droplets. So we have the heat of vaporization. The heat of vaporization is the energy required to vaporize 1 mole of the liquid. And it depends on the intermolecular forces again. So if you look at the heat of vaporization, it's always going to be positive. It's always endothermic. And the reason why, or can someone tell me, why is it always going to be endothermic? Exactly, right. It requires energy to go to liquid to gas. So energy needs to be inputted into the system to break those intermolecular forces of the liquid to turn them into a gas. Exactly. So we have our vapor pressure here. So water has the highest vapor pressure, or sorry, vapor heat of vaporization, because it has the strongest intermolecular forces. So that makes sense. And then we have isopropyl alcohol. Acetone is very weak. Then diethyl ether is even weaker, and which is very similar to acetone. Well, not really. I mean, here's diethyl ether. Well, I'll just draw it like this. You have O, CH2, CH3. Then you have CH2, CH3. It's a little bit more nonpolar than acetone, which is why it has a lower heat of vaporization. Any questions on that? Let's go on. All right, next. Vapor pressure. So I talked about this already, but basically the pressure exerted by the vapor when the substance is in dynamic equilibrium with its liquid is called the vapor pressure. The weaker the attractive forces, the more molecules would be in vapor. That makes sense, right? Because if you have acetone, immediately when you spill it, a lot of the molecules already move to vapor. So therefore, the pressure in the vapor of acetone is going to be larger than something like water. So what this means is the weaker the attractive forces, the higher the vapor pressure. And something you'll have to do in the homework for chapter 12 is be able to rank molecules based on their vapor pressure, based on their attractive forces, based on their heat of vaporization. So it's important that you understand these concepts. Just to recap, we know about the forces, but vaporization in general, the heat of vaporization, that's the first one, is the energy required to vaporize a mole of liquid. The lower the less forces there are, the lower the vapor pressure, the vapor heat of vaporization. The more forces there are, the stronger forces there are, the higher heat of vaporization. Vapor pressure is the opposite. The weaker the forces, the higher the vapor pressure, because more of the liquid becomes a vapor, not requiring much energy because it's very weak interactions. There's nothing really holding it together. It becomes a vapor. And then the stronger the attractive forces, the more in a liquid it wants to be. So therefore, not much of it will go to a vapor, and it will have a low vapor pressure. And this makes it more volatile. So volatile, think of the word volatile. What does that mean? It kind of means hostile, dangerous, right? So volatile means it gets to a vapor quickly. So think about which one can hurt you quickly. Something that's sitting there with a low vapor pressure or a high vapor pressure. High vapor pressure, because it becomes a vapor and it could get to your eyes or your lungs. So that's going to be more volatile. Okay, moving on. And then boiling point. So boiling point is another thing that, and really the definition of boiling point is where the temperature of a liquid reaches a point where the vapor pressure is the same as the external pressure. So what that means is that you have, and it's directly related to your intermolecular forces, right? So the association real quick is the higher the boiling point, the more intermolecular forces you have, the stronger forces. Lower the boiling point, weaker the forces. So if you have the pressure of your surroundings, your external pressure is the same as your vapor pressure, meaning your liquid can now all escape into a vapor. That's when it starts to boil, because the pressures are equal. There's no higher pressure of the surroundings pushing the liquid together anymore, since you heated it up to a point, the boiling point, where it is allowed to intermingle with the other gases that are in the environment. So in other words, you're heating it up until it makes bubbles. The bubbles mean that the pressure of the liquid is now the same as the external pressure. Then they mingle together and become a mixture of gases. Good? Okay. All right, boiling point, we talked about that. Heat curve of a liquid. So we kind of talked about this. We know Q equals MC delta T. Vapor pressure versus temperature. So as the temperature increases, the vapor pressure increases. This kind of makes sense until you get to the boiling point. Here's the charts for different substances. So vapor pressure. We'll look at a couple right now. Ethanol. Ethanol is right here. So ethanol has a relatively high vapor pressure when compared to water, because it's more nonpolar than water. So it will have higher vapor pressure at room temperature. So let's just say, or at any temperature. So let's say we have the vapor pressure here. So if you increase the temperature, you have more vapor, because you're kind of slowly breaking those intermolecular bonds. More of the ethanol is becoming vaporized until you get to the boiling point, which is right here at 68.1. And then it even shoots up more exponentially. That's because now more molecules at a faster rate, almost instantaneously at that temperature, are becoming gaseous, are becoming vaporized. In water, that process takes longer, 100 degrees. And then for, what do we have here? Chloroform. Chloroform, the boiling point is probably in the 40s. Yeah, acetone, it's like 40. These are all like in the 30s and 40s. And like the dichloromethane that I talked about before, its boiling point is like 37 or something. So, okay, moving on. Next thing. Oh, that's a problem. What's that say? Oh, there's more stuff in there. Okay. All right, we have a bunch of stuff. So this guy, these guys, the Clapeyron equation. I hate saying that. I just call it the Clapeyron equation. The Clapeyron equation. It's an equation that can tell us the vapor pressure and temperature of a solution based on the pressure or the temperature. So I'm gonna edit that out. Okay, what it is is we can find out the heat of vaporization using the slope. And the slope tells us the energy per mole, of course, because we're doing this all in per mole, per degree. So the energy required per degree of the vaporization. So let's just take a look at what the equation is, first of all. Here's the equation. So what we can tell is the heat of vaporization at, if we know the difference in temperatures of one substance and we know their pressure at two different points. So if we know the pressure and temperature at two different points of a substance, we can figure out its delta H, vaporization. And R, so R is our ideal gas constant, but it's a different R now. So now we're going to use the thermodynamic R, which is 8.314. So how you would solve this? You have pressure number one. So let's say you have a substance that has a pressure of 1 atm, as a vapor pressure of 1 atm at 25 degrees. You would be like, all right, P1 is 1 atm. T1 is 25 degrees in Kelvin. And at 20 atm, it has a temperature of 200 degrees Celsius. So you'd say, all right, P2 is 20, T2 is 200 plus 273 to make it Kelvin. From there, you know what R is. R is 8.314. You'd be able to calculate the heat of vaporization of that substance from that. Clausius-Clapeyron equation. Yeah. Any questions on that? Kind of just plug and chug. Pretty easy. Okay. So supercritical fluid. All right. So kind of involves with getting like in the mixture of the phases here. So as a liquid is heated in a sealed container, more vapor collects, causing the pressure inside the container to rise. The density of the vapor increases, right? Because you have now more gases in the headspace. And the density of the liquid decreases because you have less molecules in the liquid. So at some temperature, the meniscus between the liquid and the vapor disappears and the states are commingling. This is called a supercritical fluid. So it's weird. And I don't think in a lab setting I've actually done supercritical fluids, because you need a pretty, usually there's not many liquids that can maintain this for a long time. Usually it just goes from one to the other, but it's possible. So basically you have a liquid that it's kind of hard to explain. Like, it all becomes a gas, but it's high pressure to the point where there's still liquid there, but it's like there's no meniscus. It's just kind of like it's like a gradual. There's still liquid at the bottom, but it's like a gradual change from liquid to gas. So it's weird to explain, but you can look it up. Look up like right here's the picture. Here's what it would look like. So you see the clear meniscus there, and then you see the meniscus kind of disappear, turns into like a gradient of liquid down here to gas up here. So it's kind of like just a gradient. There's no dividing point, put it that way. So this happens at the critical point. And there's a critical point on the graphs. So I'll show that. Where's the critical point? Here we go. So here's what a normal phase diagram looks like. So here's the critical point. It's the point at which the temperature meets the vapor pressure of the liquid, or makes the, so it's the point at which the temperature, let's go back to the definition. I don't mess it up. I don't want to say it wrong. So it's the point at which how do they say it? So the temperature is required to produce a supercritical, whatever. So the pressure at a critical temperature is called the critical pressure. And a critical at a critical temperature or higher temperatures, the gas cannot be condensed in a liquid. Okay, cool. So basically what's happening is, let's go back to the graph. Here we go. So the temperature is at a point where the liquid's pressure is equal to the gas's vapor, or the liquid's vapor pressure is equal to the gas's vapor pressure. Therefore, their pressures could intermingle. But you cannot go higher than that. Well, the molecules can't go higher than that, because then it would either explode and it would go back to equilibrium, or that's it. That's really what would happen. So it's weird. It's a weird point. Also, you have the triple point. So triple point is important too. So it is a temperature and a pressure at which all three states of matter of that substance intermingle at the same time. So that's weird. I'll see if there's a video on that. After we're done, I'll see if there's a video on that. So I want to see that. And I think it's good for you guys to see that too. So yeah, I mean, that's about it. Heat of fusion, it's important. Is it? Let's see. Heat of fusion. So the amount of heat, we kind of talked about this, right? So heat of fusion is melting. So if we want to melt 1 mole of a solid, it's called the heat of fusion. And it's really represented by, if you want to go from the heat of crystallization, so crystallizing means you're going from a liquid to a solid. So the energy negative of that is the heat of fusion. Another way you can figure it out is the heat of sublimation. This is not too important, but heat of sublimation is when you go from the energy required to go from a gas directly to a solid. So that's all the way. You're going from one extreme to the other. If you have the energy required to go from a gas to a liquid, or sorry, a liquid to a gas, which is the vaporization, that's one of those steps. So if you take the heat of sublimation, subtract the heat of vaporization, you end up with the rest, which is the heat of crystallization, or the heat of fusion, or the negative heat of fusion, same thing. So you're kind of getting into 2 steps. So I'll draw that in a, just so you can understand. So you have gas, liquid, solid. Gas to solid is delta H sub. Liquid to gas is delta H vap. And then so to subtract delta H sub equals, or delta H sub minus the vaporization equals delta H fusion.